Ya, baik Bapak-bapak, Ibu dan adik-adik mahasiswa, sebelum kita mulai acara kita pada hari ini, kita barangkali sesuai dengan tuntutan admin fakultas kita foto bersama dulu ya. Oke, silahkan maju ke depan barangkali kita mungkin. Ya, ya. Oke, kita akan mulai workshop series pada hari ini ya. Jadi saya agak kombinasi bahasa Inggris barangkali dengan bahasa Indonesia. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah wassalatu wassalamu ala asrafil anbiya'i wal mursalin Sayyidina Muhammad wa ala alihi wa sahbihi ajma'in. Amma ba'du. Jadi puji syukur atas perkenan Allah Subhanahu wa taala kita bisa menyelenggarakan salah satu agenda fakultas pada hari ini, yaitu workshop series mengenai artificial intelligence and sea condition for marine and environmental sciences. Sebelum saya lanjutkan barangkali ke ini, saya akan memperkenalkan dulu pemateri pada hari ini ya. Jadi yang dekat adalah Maram Esa Maldin, S3 candidate for Kyoto University. Kemudian dia bergabung dengan Ocean Ice, perusahaan Ocean Ice sejak 2022 sampai sekarang sebagai software engineer. Kemudian yang sebelahnya adalah saudara Theodosius Januarsah Sadikin. Jadi orang Indonesia yang juga bergabung dengan Ocean Ice dari Risumekan University. Nah, selanjutnya saya mencoba mengantarkan juga dalam bahasa Inggris ya. Jadi good morning distinguished speakers from Japan, especially from Ocean IS company. Respected college researchers, students, and all participants. On the behalf of Faculty of Marine Science and Fisheries, it's my great pleasure to welcome you to the workshop series titled Artificial Intelligence and Sea Condition for Marine and Environmental Sciences. Thank you very much for taking the time to join us today. The rapid development of digital technologies, particularly artificial intelligence and satellite-based ocean observation system, has opened new opportunity for advancing marine and environmental sciences. Today, researchers and practitioners can access vast amount of oceanographic data and apply advanced analytical tools to better understand marine ecosystem, monitor environmental changes, and support sustainable fisheries management. This workshop series aims to introduce participants to the integration of ocean observation data and artificial intelligence techniques, and how these technologies can be applied to address real-world challenges in marine and environmental sciences. Today's workshop will be consist of 2 sessions, each providing valuable insight into emerging tools and approaches that support marine research and fisheries applications. Okay, we will begin with our first session titled Introduction of Ocean IS View for Sea Condition and its Utilization in the Fishing Industry. In the session, participants will be introduced the concept of the observation the ocean from satellite perspective, often referred to as the ocean IS view. Through remote sensing technology, scientists can monitor key environmental variables such as sea surface temperature, salinity, sea current, ocean current, and other oceanographic indicators. This data play a crucial role in understanding marine environmental dynamics and have increasingly used to support fisheries operation, identification of potential fishing ground, and decision making in the fishing industry. Okay, it's my great pleasure to invite our first speakers for this session to share their knowledge and experience. Please join me to welcome in welcoming our speakers. Okay, sorry.
Test. Hello, everyone. Thank you very much for coming today. My name is Theo. I'm from Ocean Ice. I'm originally from Indonesia as well, but I will do this presentation in English. If you have any question later on, you can ask me in English or in Indonesian. So for the first session, I would like to talk more about our mobile application called OEView, and I would like to explain more about how we can utilize sea condition data in the fishing industry. For today's agenda, I will explain first about our company Ocean Ice and who we are, and then I would like to show you a case study of how we created a potential fishing ground forecast using AI technologies and sea condition data. Also, I would like to introduce you about our mobile application or OEView, and also its differences with other data sources, as well as how the data sets that we provide in OEView and how you can utilize these data. Later on, we'll have a Q&A session as well. And then I would like to ask everyone to answer a form at the end of the presentation. To summarize, Ocean Eyes utilize sea condition data and fish catch data. And with this data, we created an AI model for finding the best fishing locations. We mostly work with fishermen as well as fishing companies. And also, we created the OEView mobile applications where our users can access this data free of charge. And also, we have the premium version as well. I will explain more about it later. So before we start with our presentation, I would like to have the audience to download our app first. Which, if you wouldn't mind, please scan the QR code. The QR was closed by the hour, but he changed it now.
Maybe you can zoom in.
I don't think I can see.
Zoom in and go to the right. More, I think. It's not showing on the.
Ya, jadi hadirin yang bisa barangkali dicoba untuk menggunakan aplikasi ini bisa langsung di-download di barcode ini. Untuk kita coba bagaimana misalnya mengamati kondisi laut mungkin di sekitar Sulawesi ya.
You have to press all the time.
Langsung dari aplikasi.
Turn it on now, right?
It's turned off now.
Yeah, now it's on. It's red.
Yes, but you have to press it if you want to.
Really?
Yes.
Ya, seperti dijelaskan tadi ada beberapa bagian yang pre-download, bisa kita download datanya langsung. Nanti juga ada khusus yang premium, kapasitas premium begitu.
Oh, like the person did the crop the QR code for the screen.
Okay.
Should we continue? I think everyone done.
Sudah dicoba untuk iPhone yang di atas ya, di Android yang di bawah.
Okay. Did everyone everyone downloaded already? Okay. So I will continue with the presentation. I would like to explain a little bit about our company, Ocean Eyes. We are a Japanese company, and we were established back in 2019. So we have been operating for almost 7 years now, and our current clients are mostly local municipality in Japan, such as Tokyo, Chiba, and Shizuoka. Also, we have been working with a fishing company in Indonesia as well. They are called Kapikan, and they have about 3 vessels operating in north of Sulawesi right now. And also, here are our founding members, our CEO, CTO, as well as the directors. They are mostly researchers from Kyoto University, as well as from JAMSTEC, which is Japan Marine Science and Technology Department. Here is a case study that we did a couple years ago. This is on the east side of Japan, sea of Japan on the east side. And here in this example, we created a fishing ground forecast for squid. And the area with the pink color have the highest probability of squid catch, and blue is medium, and white is have a low chance. In this case, fishermen, when they get the map, they could go straight to the pink pink areas to find squid. Also, our mobile app OEView, it provides sea condition data, and it's readily available, and it updates every 24 hours, so you can check the latest data. And also, we provide data from different depths of up to 200 meters deep. And then also, we cover all sea area in the world, not just Japan, but also Indonesia, Malaysia, and other countries as well. And also, our app can be used offline with our download function. And right now, it's available in English, Japanese, and Indonesian as well. Also, how our app is different from other data sources. First, we provide AI cloud removal on our analysis. So from the sea condition data that we gather using satellite, there are some areas covered by the cloud, which the satellite couldn't record. We use AI cloud removal in order to provide data for the areas covered in the cloud. Also, we use multiple sources. We use satellite information from Japan, Europe as well. And also, we provide forecasts of up to 3 days. So you can also not just check the past and present data, but you can check the forecast as well. Here is one of our research for our AI cloud removal. If you can see on the first graph on the right side, that is the comparison between data caught from the buoy compared to data caught from Himawari. The accuracy is quite precise, but when it comes to areas covered in the cloud, we have to use the AI that I mentioned before in order to generate the data. And comparing it to the buoy data, it's not as good as when it compares with the Himawari satellite data, but it's good enough for our analysis. And here is an example of the data that we gathered. There are 2 areas in this example. One is in south of Java, and the other is in southeast area of Japan. As you can see from the graph, it's logical, since in Japan the temperature can go down of up to 20 degrees in the winter, and then while in Indonesia the temperature doesn't change as much. The range can be from 26 to 30. So I would like to show you some of the data sets that's available in our mobile app OEView. One is the sea surface temperature. I will explain a little bit more about each of the data set, and then I will show you also how to navigate the mobile app later. So the sea surface temperature shows the temperature of the top few millimeters of the ocean surface water. And we can utilize this data for locating fishing grounds, since it shows the suitable habitat for different kind of fish. And another data that we have is the sea current. It shows the direct movement of the ocean, and this data can be used in our potential fishing ground forecast as well, since the current is responsible for the transport and dispersal of eggs and larvae of fishes, as well as phytoplankton. Another one is chlorophyll. Chlorophyll is produced by plankton, which is the main food source of smaller fishes. We use this data as well in order to find the fishing grounds, since the fish would gather in high concentrated chlorophyll areas to find food. Another one is sea level anomaly. This data shows the height of the sea surface compared to the previous sea surface, and this data can be used to predict short-term and long-term natural disasters such as high waves and many more. Another one, which is wave height. This data shows the the measure of the vertical distance between the lowest and the highest part of the wave. However, this data is only available on Sea of Indonesia, so it only shows wave height from Indonesian area, as well as for the next data, which is wind speed. Wind speed is also only available in seas of Indonesia right now. With the wind speed, you can check the wind speed of the wind speed, and we mostly use this data in order to help vessels navigate through their fishing trips. Next, I would like to explain on how we can navigate the mobile app.
Maybe explain it here first briefly, and then we can show it now. Just explain like the main parts of the
Yes.
app, and then
I would like to explain briefly of our homepage. So here, once you open the mobile app, the red dot shows your current position, and also our app utilizes the GPS on your phone, just like Google Maps, and also you can navigate it with your two fingers to zoom in, zoom out, and move to other areas as well. And also on the bottom left side, you can choose between today, yesterday, and the forecast for the data display. And to start showing the sea condition data, first you have to download the data first. On the top right side, the green square or yellow square, it shows that if it's green, then you have the latest data. But if it's in yellow, it shows that the data is not updated yet, so you have to download it first. You can download the data from the bottom right side of the screen with the arrow. Once you press the arrow side, this screen would appear. You can choose the data that you would like to download, whether it is the sea surface temperature or the sea current. Once you click on this data set, the second screen will appear, where you can choose the depths of the data. Currently, for sea surface temperature and current, you can choose the depths of the data, but for the rest of the data, you can only choose the surface data. Once you have chosen the data set that you would like to choose, you can choose the coordinates of the area that you would like to see on the bottom side, and then on the next side, you can choose the range of temperature that you would like to see. And also, once you've chosen all the criteria, you can download the data by pressing the download button at the bottom. Also, on the top right side of the screen, there's the time symbol. You can press that button in order to show the data set that you have downloaded previously or that you're downloading right now. Once you've downloaded the data, you can go to your the home screen and press the top middle part of the screen in order to choose the C condition data that you would like to see on the app. So I would like to show you how you can use it. So right now I'm using the app on Maram-san's phone, and here once you press the top right square, which is the right now it's green, which shows that it has the latest data. But if it's yellow, then you have to go to the bottom right side of the screen with the arrow symbol.
Maybe it's the internet.
Did you change it to the?
It's the internet. Your
Wait a moment.
internet got disconnected.
Oh yes, it's working now. This is the screen that you would have seen if you press the bottom right button, and then once you choose all the data set that you would like to see,
See the internet.
sorry, our internet is quite slow. So, for example, if you want to check the sea surface temperature, once you click the temperature forecast, the water depth option should appear.
The network coverage is really low here.
Maybe we can change it to the hotspot for the
If you do
school
this,
hotspot.
everything's going to disconnect. This is the hotspot.
Oh, okay. It's okay. Let me change that one as well. this computer is using which
Here.
internet?
Click on it. Close it and try it. Okay, open the browser.
Gee, there's there it is.
Can you reconnect? Go to Slack.
Slide. Wait, where's
Oh, sorry.
Slack?
Yeah.
Yes, now we are using the school's. Should be okay now. Okay. Sorry about that. So I will try to explain it again. Once you press the bottom right arrow, uh, this screen will appear. You can choose the data that you would like to download, and as for the temperature forecast as well as current, once you press it, there is the depths options. You can choose the depths that you would like to download as well for the current forecast as well. However, for the rest of the data, only 0 meter depths can be downloaded for now. Once you've chosen the data that you would like to download, you can choose the coordinates from this part, whether it's the north part or south, east or west. And once you finish choosing the coordinates, you can press download to download the data. Once you've downloaded, the map would turn from gray to the colors of the data. In this example, this is the temperature forecast. You can press the top center button in order to choose the data that you like to see. I can change it to chlorophyll. This is the current chlorophyll data on these areas. Also, for temperature, this I can check the temperature today and the forecast tomorrow as well by pressing the +1 day. The forecast is available for up to 3 days. This is the forecast for 14 March. I can go back to the current by just pressing the latest button. Also, if you would like to check yesterday's data, you can. So once you've downloaded the data today, tomorrow you can check today's data by pressing the -1 day button. Also, you can change the depths on the top right side. Right now, that was the -10 meter depths. If I change it to 100 meter depths, you see here there are parts gray area. It shows gray because it's shallow water, so it doesn't have the data for those sites. But you can see the other part where the for the 100 meter depths. Okay. So I stop. Thank you. Are there any questions so far?
Okay. Let me show them now the maps.
Okay, we will move to the second sessions. Thank you very much to our speaker for insightful presentation, for sharing valuable knowledge on the use of ocean observation, data in fisheries and marine science. We will now proceed to our second session titled Introduction of Artificial Intelligence for Marine Environmental Sciences. This approach enables scientists to improve prediction of species distributions, ecosystem dynamic, climate variability, and environmental changes, ultimately contributing to better management and conservation of marine resources. It's now my great pleasure to invite our next speakers, Ms. Maram San, to introduce how artificial intelligence can be applied in marine and environmental research. Please welcome.
Hi, everyone. Thank you for your time and thank you for attending. So first, before we head to the technical part, I'd like to show you the outcome of some the AI model, or the results of our IAM model. So it's provided in OEView in the premium tier. So far we provide two fishing-related AI services in OEView. So as Theo just shared, we have different ocean parameters that are shared in the free tier of OEView, but as well we also have two services that are related to the fishing operations that fishermen can usually use. So in most cases, fishermen rely on their expertise and their knowledge to know where to go in the ocean. However, if they don't, we provide two kind of maps that can guide them during their operations. The first one is called a storm maps, and this map was trained using the Global Fishing Watch trajectory data, and it shows the fishermen where it's safe to operate and taking into consideration the wave height and the wind speed. The second kind of map is the tuna prediction fishing grounds map. So in the later part of the seminar, we would show you how we can start with developing a simple fishing ground map. So in this case, the model takes into consideration different ocean parameters like the temperature, chlorophyll, salinity, even the IOD indexes to show where the fishermen should head. So the output of these maps would be the likelihood of where the top 25% of the catch would be. So if an area is very likely to have high catch, this means that during the year it was within the top 20 or to 25% of the catch. This is how the maps look like outside of the app. So first, this is the storm maps. As we can see, we have a range from 0 to 1, 1 being very high turbulence or low safety. So if the fishermen use, or even navigation vessels, if they use this map, they can target the areas that are close to 0 to guarantee high safety. We can see here, for example, the yellow areas a bit deeper in the ocean. This is mostly most likely very turbulent conditions, and this map gets updated daily, so fishermen can plan their trips after checking this map. So after where it's safe to operate, the fishermen are mostly interested in knowing where or what areas have high catch amounts. So this is the second PFG maps, the prediction of fishing grounds. In this case, also we show an index that shows likelihood of high catch. So here we can see the orange areas. These are areas that most likely has very high catch, or the top 25% of the whole annual catch. So using these two maps, the fishermen, even without having previous experience or knowledge about what areas has high catch areas or fishing hotspots, they can use these two maps to navigate and head to the areas that are both safe to operate, but also has high catch as well. So far our experience with the AI or PFG forecasting, we compared for our initial client the profit or the catch that was caught, the fish that was caught, between the traditional methods as well as using the PFG. So our base model initially increased the profits with 21%. And as we can see here, the catch that was recorded using the traditional approaches is much lower than the ones where we use the AI PFG models. And that was our base model. Recently, the more accurate fish catch that we have for training our models, the accuracy of the model increases as well as the profit made by the clients. Also, the fishermen using the application, the PFG maps, they reported 5.5 out of 7 on how useful the PFG map was for them to guide them to high fishing areas. Right now, these two services are available in our application in the premium tier. So everyone who signed up for the application, you can sign up for the premium tier and you will have 2 months of free usage. So I would like to show on the app where here, Theo already showed the different tiers of the temperature, the ocean parameters that we can see on the application. Once you sign up for the premium tier, on the left here, you can sign up or manage your subscription, and you will get to sign up for the premium and get 2-month trial without providing any payment services. Once you sign up for that, in the main window, 2 extra services would be visible to you, the Big Eye Tuna and the store map. So when we show the store map, it will show us the areas that are safe to navigate and the areas that aren't. Here we can see the areas approaching 1, or the red areas are dangerous areas to operate on that specific day. We also have on the lower bottom, we can see the forecast for the following 3 days on how the storms are likely going to change, and then make navigation decisions based on that. The second kind of map is the Big Eye Tuna. This will show us the predictions for the amounts of fish predicted. So here we can see the areas that are closer to red. These are the areas that will have much higher predicted catch. So combining these two maps, the fishermen can navigate and decide for the following days what are the optimal areas to navigate to, as compared to previously their traditional approaches of asking other fishermen or going to the same locations they went to in the previous seasons. Okay, this is it for introducing our application. If you have any questions, please feel free to ask or share any insights. Maybe ask them about to fill the form if they don't have any questions.
How about the methods you use to develop forecast?
So we will introduce it in the session after. So once the Q&A is over, we will introduce the second part of the AI workshop.
I think this time also we can use this time as well. We
Okay,
have,
so ask them to scan the QR code.
yeah, I think we have enough time to.
Yes, so
Continue.
before we start the AI session, I would like to ask the audience to scan the barcode on the screen, and it will goes to Google form. It only have about 4 questions. It only takes 5 to 10 minutes to answer the questions. We would like to have the audience to answer those questions. Thank you.
Theo,
Yes.
maybe the microphone.
We will open the discussion session first. Okay. We will now open to discussion session first. I think before we continue to application of artificial intelligence. Okay. First, just tell your name and also questions.
Assalamualaikum warahmatullahi wabarakatuh. Thank you very much of opportunity. So I am Rizky Onalwi. I have been graduation in Master Science, specifically in remote sensing coastal area. So I want to ask about the challenges is challenges and in the future the application based on data, because I know the ocean is very dynamic to make decision the catch or the fishing ground in the ocean. So how is the challenge in the future to make a good develop in the future based on application? Thank you very much.
Okay, thank you so much for your question. So, as you probably know, like you mentioned, the ocean parameters are really complicated. So it's very difficult to decide how or what exactly affects the fish distribution from year to the next one. And sometimes we have effects that are extended to a couple of months or a couple of years, like the climate events. But in this case, training a model to predict the fishing grounds, unfortunately, the most challenging part is not the sea conditions, but the quality of the data. So usually in the AI approaches, like we'll see in the AI session, it's all about finding the patterns between the catch data and the different sea conditions. So usually we start with assuming or researching what kind of ocean parameters affect the catch, and then we train our model based on this. However, this relies a lot on the quality of the satellite images as well as the catch data. So far, the satellite images we have very accurate satellite records for the ocean parameters, but the records of the catch are usually not accurate. Sometimes it's because of the expertise of the fishermen. Sometimes they record it after the fish start moving. Other times it's also because they don't want to report where is the high catch areas. So this results in us trying to train the model, the relationship between the ocean parameters and the catch, but in this case, the catch is not accurate. So although initially we would think that it's difficult to find a model that structure that can work with our sea conditions, but in reality, the challenge lies more in the quality of the data more than the technology itself.
Thank you.
Thank you
Yeah,
so
I
much.
think sometimes fishermen consider this confidential data to distribute fishing position, the real fishing position. Okay, next to the next question.
Thank you very much.
Thank you.
I would like to ask you about is it possible that we get your data at the narrow area? Because most of our students work in a narrow area, for such as Losari Beach, sea near the Baranglompo Island.
Yeah.
So, is it possible to get data in the narrow area?
How narrow is the area?
For example, 10 kilometers. 10 kilometers.
Yes, so in this case, you will be able to see it. So right now, the resolution of the maps is 8 kilometers per pixel. So anything greater than half of that area, so anything greater than 4 kilometers, you will find a pixel that shows the different temperature, the storm map, even the PFG related map. It will show you the amount in that area. So even if the area is really small, it will show as 1 pixel, but that 1 pixel would have the value that you need.
Can you show the example
Yes, sure.
about the temperature in Losari Beach
Yeah,
in
sure.
Makassar, West Makassar?
Can they put the... Yeah, okay. 1 second. Okay, so Professor, would you like to navigate? Which area are you interested in? So zoom in. Okay, so I think this was the area of your
Yeah.
interest. So here in this area, you can see, for example, when we check the temperature at 0 depth, most of the area shows to have values. If we go deeper, because this is a shallow water area, it will show you that this doesn't go deeper than 10 meters, so it doesn't have any temperature. And the deeper you go, the more shallow areas appear. So if you're interested in these narrow areas, the surface temperature and the surface current are always present. So you can see him here as well as in the current. I think this was your area of interest, right?
Yeah, okay.
Yes, so anything bigger than 4 kilometers, it will show, because right now the resolution of the pixel is 4 kilometers for the ocean parameters. So anything around that size or around that area, it will show to have values. Maybe it wouldn't have deeper layers because the water is shallow in that area, but it will show the surface levels.
Okay, thank you.
Thank you.
Well, is it possible to use finer resolution such as Sentinel 300 meter to this? I mean, to these applications.
I think it's possible, but maybe for the forecast, because for the forecast was using the Mercator resolution. So we already increased the resolution from 8 kilometers to 4 kilometers. So for the forecast, anything less than 4 kilometers won't be apparent. But for the same day, we can use the Sentinel data.
Yeah.
Because as you know, the Sentinel data, it has some delay. So
Okay.
it's not updated on a daily basis.
Okay. Any other questions? Okay, I think to make more efficient times, we will continue to artificial intelligence sessions.
Yes.
Okay.
Okay, maybe we can stop Zoom now. We don't need it. Maybe you can stop Zoom now. We don't need it. Oh, okay. Okay, so the second part of our session is introducing the use of AI for marine sciences and environmental sciences. So before we get started, I would like to ask who here has any background in programming.
Is there any good background in programming, air language or MATLAB?
Yeah,
My
any
research
language.
in artificial neural network, I use MATLAB.
Oh, okay. So MATLAB.
Yeah,
Okay, so let's get started then. So first, you can scan this QR code. It has all the materials for the workshop. Later on, if you want to experiment with the code further or check some of the data set, it's always available in this QR code. Okay, so before we go over the topics that we'll be covering, I would like to discuss the format of this session. So first, the first part will be a theoretical part. We will go over some of the concepts that are necessary or needed to explain the AI. And then the second part would be a guided tutorial. So it would be, as you see in the link, notebooks that already have code, and we run the code. And then we will go over, if we have a problem and we have a data, how we can start progressing, or how we can start developing an AI model to solve that problem. So the topics that we'll be covering in the theoretical part of the session is, first, what is AI, what is machine learning, and what is deep learning, and what they can realistically do. And then we can cover some concepts related to each, as well as working with spatial data. So the goal of this workshop is not to become experts in programming or to cover the technical part of it, but I would like for us to think together about, even if you don't have any technical background, even if you don't want to specialize in technology, how you can utilize the technology and use it to solve some of your problems. So as you will see in the guided tutorial, I divided the notebooks to show some codes and explanation of what each code segment would do, so that later on, even if you don't have the technical knowledge, you can still change the code slightly to work with your data set. And as we all now know, probably all of you use ChatGPT or Claude or Gemini for different purposes. So now you can utilize this for learning or for solving problems using your data, even if you don't want to get too deep into the technology or get bothered too much about the syntax of the code. So you can gradually, even before you know too much about the technology, you can start experimenting and seeing how it can solve your problem, and gradually get more familiar with the syntax and the technology. So in this case, for marine sciences specifically, why is AI becoming important? As you know, in marine or environmental sciences, we have a lot of large data sets. They usually have complex relationships between multiple variables. So AI in this case can help us analyze data sets that have multiple dimensions. It can also help us detecting patterns between variables. Sometimes we know that variable X and variable Y have a relationship, but we don't really know the mathematical or the physical equation or the specifics of the relationship. We just know there is a pattern. In this case, AI can help us detect these patterns and generate predictive models that can help us get forecasts for the future. But in this case, it's necessary to highlight that AI does not replace domain knowledge. It just supports the scientific analysis. So to develop any model, the most crucial part is the knowledge that you have about your domain. So in your case, the knowledge that you have about the marine sciences, about the ocean, about the different parameters is more important than the technical part. So you start with this knowledge to design your solution. So what exactly is AI? So AI refers to any computer systems that is designed to perform tasks that usually would require our intelligence. For example, recognizing images, detecting patterns, making predictions, even identifying the relationships between variables. AI can help us with that. So the relationship between AI, machine learning, and deep learning is that they are subsets of each other. So AI is the big group, any system that requires intelligence. Inside that, we have the machine learning. So machine learning is a set of algorithms that can help us detect patterns from data. So instead of explicitly programming the relationship between X and Y, I just give the machine learning the data, and then it learns the patterns from these data. Finally, the deep learning is a subset of machine learning where the data is complex. So if we have data that has multiple layers, multiple dimensions, and they're complicated, they have locations, they have images, in this case, we use deep learning. So all of the concepts that apply to machine learning, they apply to deep learning as well. It's just a one step deeper or one step more complex. So realistically, what can these methods do? So we would suggest using AI or machine learning when we have a pattern that we want to detect, especially in large data sets. If we want to learn any relationship between variables, if we want to perform classification, recognition, regression. So anything that would help us find these patterns and then make a scientific decision, we can use AI for that. An example for that is classifying environmental conditions or detecting patterns in our satellite data, even predicting fish habitat suitability. Realistically, we can use AI for that. So in this case, the model learns from the correlation of the data, not from the physical law. So even if we have the relationship, the mathematical relationship or the physical relationship, it's not really important in this case. The model would learn from the data itself. That's why we mentioned earlier that if we have a flawed data set, the model would be flawed as well, because we don't give it the equation, we just give it the data. So some common misunderstandings when we're developing our model is that if we have data, magically the AI will understand our system. That's not correct. Also, there's a misunderstanding that the more complex the AI is, the better results. That's also not correct. Usually we will start with simple models, evaluate the results, and then we get more complex. So usually we start with the most basic machine learning algorithm. Then we also have the misconception is that the higher the accuracy, the more our science is correct. So sometimes if we lack the domain knowledge, we can design a problem that's not correct scientifically, but we will still get very high accuracy or better results. And the last misconception is that more data automatically will solve the problem. So sometimes if we have really low metrics for the performance of our model, just dumping data on that model is not going to magically make it better. So why the data quality and the problem framing matters? So the machine learning performance usually depends on three crucial parts. The first part is the quality of the data. The more noise, the less accurate our model would be. The second part, if we don't define our problem correctly. So sometimes we know that we want to predict something, but the solution is not well defined. In this case, the model is not going to perform well. And finally, choosing the appropriate variables. An example of that, let's say we want to predict the rainfall over a certain area. We know the appropriate variables is most likely the humidity, the temperature, and so on. But if we choose variables that are not appropriate for this problem, the solution is not going to be as good. Also, some of the issues that we have with the data is sometimes we have biased data set. So if we want to predict a fishing ground map, and we take the fishing data sets from very specific location, in this case, our data set is biased and will provide biased predictions. So we cannot, in this case, take it and generalize it to everywhere else. The second part is the missing values. A lot of times, the fishermen don't record the catch. In this case, we won't know how to deal with the missing data in our data set. Do we remove them? Do we fill them? So in that case, that also needs some analysis. And finally, how well we define our target. So the well-defined scientific question is usually more important than the model itself. Very clean data set, properly defined solution, and choosing the right variable based on your domain comes with the highest priority. So some concepts that apply to machine learning that are necessary for programming. First, what kind of machine learning algorithms or learning paradigms are there? So we have three main learning paradigms in machine learning. First, if we have both the input variables and the output variables, this is called supervised learning. An example for this, if we want to predict rainfall, the temperature, the humidity, the wind are all present, as well as the rainfall measured. In this case, this is supervised because we give the model both the inputs and the outputs and wait for it to make recognition for the pattern. In the second case, it's unsupervised learning when we don't have the label or the target of the data. For example, if we have different locations in the ocean and we want to group them together based on sea temperature or salinity or nutrients and discover the regimes in the ocean. In this case, we don't really know what labels or what these areas are, but we just want to group them together. In this case, this is unsupervised learning. And finally, the semi-supervised learning is we have a combination of both labeled and unlabeled data. So we have some data that we know the output or we know the label, and some data we don't know the label. In most scientific research, the supervised learning is the one that's used because it's the most applied-wise, but also we have the output variables, so evaluation is easier. So for our tutorial, we'll be following the supervised learning paradigm. So what kind of data set is used for machine learning? Any data set that you can put in a table, this is the kind of data that's used. For example, if we have these variables, temperature, chlorophyll, salinity, current, wind, we notice that each variable has one observation. So in each row, we will have one value for each variable. In this case, this is the data is called tabular data. Machine learning is known to handle tabular data well. If we want to use more complex data, in that case, we will use deep learning. But if the data, we can put it in a table, in that case, we will use the machine learning. So machine learning models will use the relationship shown in this table, like for the variables shown in this table, to make our prediction. So how do we get started with any machine learning workflow? So the first step is that we have to define the research question or what variable we want to predict. The second part is we collect and clean our data set because that's the most crucial part for the quality of the model. And then we can explore and visualize our data to be able to tell some patterns that are present. After we have clean, organized data, we can start training our model. So after we have clean and visualized data, we can start training our model and then evaluating the performance. Finally, we will interpret the result based on our domain or based on our problem. The second part is that once we have the data, we cleaned it, how do we approach with the training? So in any machine learning algorithm or any deep learning algorithm as well, the best approach is that we have to divide our data set into train, validation, and test. Similar to how when we study for an exam, the first part would be going over our notes. So we already have the knowledge, we go over our notes, we check the examples. This is the training data. So we already have solved examples, we use it to learn. This is the data that the model used for learning. So the first step is the training data set. The second part is the validation data set. So the validation data set is similar to how when you are, after you study, you go over some exercises to evaluate, did you learn well or not? This is the validation data set. And finally, the test data set is the one that's actually used to evaluate the final performance. So this is similar to how when you go to take the test and finally evaluate how you did on a single course. So any data that we have, we split it into these three parts: training, validation, and test. The model checks the training data set first, learns something, goes over the validation to evaluate is it learning properly or not. And once the training is done, the model uses the test data set to evaluate the overall process. This is necessary for the model to generalize beyond our training data set. Because now if we want to train, let's say, a model to predict a certain ocean parameters, we want the model to be able to be used beyond the time period of the training data. So we want to use it next month, the following year, the year after that, over all different regions. So in this case, the more well spread our data is, and if we split it this way, we can make sure that our model generalizes beyond just the training data set. Another concept necessary for machine learning is the loss function. So a loss function is how well or how wrong our predictions are. For example, if I make a guess on a number of something, if I calculate the error, is the difference between the actual value and my predicted value, this is called a loss function. For example, if you take an exam and you get 90 out of 100, for example, in this case, your loss function is the difference between the correct answers and your answers or your predicted answers. So in any learning problem, we need a loss function so that the model can know how well is it learning And the goal in this case would be to minimize the loss as much as possible during training. This is how we monitor our learning process. So after every turn, if the model is minimizing the loss, that means it's heading in the right direction. If the loss is increasing, that means it's heading in the wrong direction. An example for this, if we are predicting a number, the loss function would be the squared error or the absolute error. And if we have a classification problem, a loss function would be called a cross entropy. Another concept that usually happens because of the suitability of our data is overfitting and underfitting. So an underfitting is when our model is too simple, but it cannot capture any pattern in the data. So earlier we mentioned that we have three subsets: training, validation, and test. Underfitting is when the model doesn't even learn from the training dataset. This would be similar to when you are studying for an exam, you don't even understand the notes. You can't understand the examples. So in this case, this is underfitting. And overfitting is when the model learns the training dataset, but it doesn't perform well outside of this. The equivalent of this is when you understand the notes, understand the examples, but when you want to solve some exercises, you always get the answer wrong. So in this case, you are overfit on the examples that you studied. You cannot generalize outside of that. So our goal is to find a model that can recognize the pattern, but can generalize to outside of that. So you solve some examples that enable you to get good results in the test, even if the test brings new problems. Another problem is the class imbalance. So a quiet known phenomena is the imbalance of the data set. So as you can see these circles, these are different classes, let's say. So we can see that the red circles are not as common as the blue ones. So in this case, we can say, for example, this is a rare event. In this case, the model most likely would be biased towards the blue ones, because statistically, if the model makes a guess that this circle is blue, it's most likely to be correct than guessing it's red. So in this case, we have to handle class imbalance, or make sure that the dataset that we provide to the model is not biased. There is equal representation between the different cases. Another distinction that we have to make in machine learning models is distinguish between the correlation and the causation. So this doesn't just apply to machine learning, it applies also to any other scientific interpretation. So for example, we know that chlorophyll correlates with fish presence, but it doesn't necessarily mean that the chlorophyll causes the change in the fish presence. So this distinction is very important when we are making the interpretation of our model results. During training, even if we have different variables and we are studying the relationship between the variables, machine learning gives us a way to check the importance of the features. So while we're training, the model can tell us that in this case, the most important variable that was used for training was chlorophyll, and then it was temperature, and then it was depth. So in this case, we can check how important our features were during training. And the question that we answered earlier, why environmental or marine predictions usually have uncertainty, it's usually because we don't have enough data sets. We have a lot of noise in the measurements, and also a lot of our environmental variables can be missing sometimes during training. So what we can do is that we can make sure that our machine learning predictions are interpreted as approximations more than an exact values. So moving on from the machine learning concepts to the spatial environmental data. So in marine science, most of the data that we deal with has some location information embedded. So in this case, it's called spatial data. An example for this, if we have a map showing us different concentration for the air pollution, or a map showing us how the different rainfall is distributed across different areas, all of these data, the location is crucial, so they're called spatial data sets. And the format of this data set is usually has something like this. So we will have longitude, latitude, time, depth. So it has multiple dimensions, not just 2 dimensions. And the format can be netcdf, GeoTIFF files, so different kind of format of data. So this kind of data, machine learning struggles with them. Why? Because they are extremely complicated, or they have a lot of dimensions. The data that we just mentioned now has longitude, latitude, it has time, it has depth. So in this case, the machine learning approaches doesn't do well with these cases, and the solution is to use deep learning. So what is deep learning? So because of the problems that we had with machine learnings with complicated data sets, deep learning introduced something called neural networks. So a neural network is something that's inspired by our brains. So it's assumed that in our brains we have millions of neurons, and each neuron has very small set of information. So how human intelligence is perceived to work, that each of these neurons with very small set of information communicate with each other and make new deductions or new knowledge. So to replicate this kind of logic, to make sure that the computers can work or something similar, we have convolutional neural network. So they are also similar to how our brain works. We have millions of small neurons, and each part checks very small part of the data. That's why it's suitable for images, it's suitable for spatial data. Anything that has a lot of information embedded on it, we use convolutional neural network to make sure that each neuron can get small part of the knowledge and then communicate with each other. This is widely used in satellite images analysis, environmental data analysis. So the advantages of using deep learning is that we can extract a lot of features. So we have big data sets, complicated data set, we can extract the feature. Technology works really well with images and with spatial data sets, and it can detect the complicated patterns. But the limitations is that usually they require much bigger data sets, and they are computationally expensive. Sometimes they might need a GPU. Also, they're called black box models because we have a lot of neurons communicating with each other. So sometimes when something goes wrong, it's difficult to interpret what went wrong and where. So we have to make sure that we validate our results properly to get generalizable results. So the takeaways of this theoretical part is that we can use different AI models or methods to analyze complicated and environmental data sets. If our data sets can be put in a table, we use machine learning. If our data set is complicated, has a lot of dimensions or relationships, like images, like spatial data sets, we use deep learning. But in both cases, it's very important to use our domain knowledge to be able to interpret the results. So these are the references. So is there any question with this part before we move to the tutorial?
Any questions about how to use artificial intelligence, especially machine learning, deep learning, to develop in application in fisheries resources? Okay, Prof. Nadiarti.
Thank you. Special for the AI. You're talking about the examples, I think, about the oceanographic data and deeper waters. What about the coastal waters with shallow waters? Is it possible to apply to use this?
Yes. So we can use AI for any kind of data sets. So for example, in the spatial data set that we just mentioned, we can have longitude, latitude, time, depth. So even if our map had mostly land regions, in this case, we can use AI for prediction. So AI has wide use. For example, if we have satellite images that even sort different land regions. Is this a forest? Is this a lake? Is this a residential area? Any kind of classification that's based on images, AI can work with that. In the case of coastal waters or shallow water areas, In this case, we can consider the values as two-dimensional array. So any kind of two-dimensional array can well be developed by either machine learning or deep learning as well. So usually we start with a simple machine learning algorithm. If the results are not satisfactory, we assume that the relationship is too complicated, and then we move to the deep learning algorithms to detect harder or more complicated patterns. But it can definitely be used with all sort of data sets. Thank you.
Okay, another questions. Maybe from students, I see maybe you have many questions about how to apply artificial intelligence, especially in research concerning in fisheries applications in marine science. Ya, silakan bisa pakai bahasa Indonesia juga kalau misalnya ada hal yang ingin ditanyakan, nanti kita translate. Bardi? Dija? Oh ya, silakan.
Thank you. Okay, the second question to me, I wanted to ask about the combine the machine learning and deep learning to a classification in the case. So, how based on your experience, what is different to use and what is the powerful in machine learning or deep learning to use a classification, and what is the weakness both of them? Thank you.
Thank you. So the weakness of the machine learning is that sometimes it can be a bit too simple. The algorithm can be a bit simple. So for example, one of the simplest machine learning algorithms we can use is regression, linear regression. In this case, the method itself has a lot of mathematical assumptions about the relationships of the variables. So in this case, that can be a limitation, because in most cases of environmental and marine sciences, we don't know the relationship between these variables. So in this case, this can be a weakness for the machine learning approaches, but the advantage is that it's very easily interpretable. So in the case of regression, we already know the assumptions about the relationships of the variables. So if we can get good accuracy, the results are easily interpretable. You can get insights about the relationships easily. For the deep learning approaches, the advantage is that even if the results for machine learning was bad, and we assumed the relationship was too complicated to be captured, deep learning approaches can step up and give you a proper prediction in this case. The disadvantage is that deep learning requires a bigger set of data set. So, for example, if you have 100 records or 200 records, in that case, that's good for machine learning, but it's not good enough for deep learning. So you need more data. But also the disadvantage is that most models are black boxes. So the training has a lot of parameters. So if something is going right or going wrong, it's difficult to interpret what data made what change to the model. So it's not easy enough to understand what's going inside the model. Similar to how you can use your hand to calculate the regression-based approaches, but also use programming, deep learning is not easy to do that, because sometimes there are millions of different parameters that gets changed every turn or every loop where you train. So I would suggest starting with machine learning. Don't add extra complication if it's not needed. If you don't get good enough results, then you can move to deep learning approaches and make the structure more complicated as you go. Does that answer your question?
What kind of the deep learning? CNN, right?
Yeah, so we have a lot of structures for neural networks. So for example, they're all based on the assumption that we have small neurons communicating with each other. So we have CNN and the convolutional neural network. How you organize or how you structure your neurons give different names to this network. So we can have ResNet, we can have UNet. How they are shaped together, it results in different kind of networks or different kind of models, and each model would have an area that it performs best at. For example, a classification. In the case of classification, it's much easier, so CNN usually would be enough. When you go a bit more complicated, then you have to start ResNet or UNet. And in some cases where time series are important, you can use a neural network with memory capabilities like LSTM, where you use not just the data from at that point of time, but you use a series of data over a span of time.
I appreciate.
Thank you.
Yeah, okay. Another questions? Ya. Prof. Nadiarti dulu barangkali ya.
Sorry. Sorry. Before leaving, because I have a class after this, I'm talking about machine learning or deep learning. I'm totally very new for this. I just usually use ChatGPT, Gemini, and so on. So how can I access this? We have to pay regularly or
For the
free, the machine learning or
not at all. So if you have, for example, if you access Gemini or ChatGPT, or you can ask for a gentle introduction into being able how to use these algorithms. So most programming languages now provide these algorithms already coded in them. So you can choose to go with Python, you can use R, you can use MATLAB. They all have these packages and the modules ready. So if you have a problem and a simple data set and you want to learn, you can start using these AI tools and ask for a simple introduction. For example, I want to get started with machine learning, and I want to use R, or I want to use Python. Can you provide a simple tutorial? And then you can start applying with the AI tool that you use. All of these tools are completely free, whether it's MATLAB, Python, R. And there's a lot of also websites like Kaggle that provides a lot of free data set. So actual real recorded data sets that span over years. And this is the website. It's called Kaggle. Maybe it's not visible now. Oh, sorry. It's okay. This is the website. It's called Kaggle.
Kaggle.
So it has a lot of free available data sets, and it's also a platform where people can start solving different problems using these data sets. Sometimes they even have paid competitions where people can compete to get the best performing model. So you can go through some of the tutorials there or some of the lessons there, but none of these services are paid. So you can easily get started. You're welcome.
Okay, next, Dijas.
Thank you so much for the opportunity. About the machine learning and deep learning, I think it's so very important for us because these machine learning and deep learning, we can collect the predicting area for fish, but we have some challenging of these machine learning and deep learning that sometimes if we are running several method, we got some like low performance. So if we got some low performance for that method, machine model, can we continue our analysis or choose different kind of the machine learning? Yeah, so yeah, thank you so much.
Thank you. Actually, this is the process that where how you get started. So let's say you have a data set. You start with trying to make your data set as clean as possible. So let's say you have catch records. You start by plotting these catch records. Sometimes the location is not accurate. So you can find this out if you find a cache location in the middle of a city, for example. You know that there is no sea here. This data is not clean. So you checking out, or for example, most of the cache records is between 100 and 300 kilo. Suddenly you see a record that says 3,000. This is obviously like some noise. So you start by cleaning your data set as much as possible. You find the missing data, you remove them. After you start with that, you can see what kind of variables you want to work with. So let's say you work with temperature. You check out research about what kind of parameters affect your fish species. Most likely you get started with the research because there are so many data types or variables that you can design in your problem. So let's say you decided on your fish species, you decided the relevant variables, then you can start with a simple machine learning approach. So let's say you start with regression. It's very simple. But most likely the results that you get are going to be bad. But this is also good because this would be a baseline for comparison. Because if you start the right away with deep learning, you won't know how well your results are. So you start with a simple approach and you split the data as we mentioned earlier. So you give the model some data to learn, some data to evaluate its performance while learning, and finally some data to test its final performance. And while you're training, you would get some metrics. So let's say you're trying to predict the fish amount. The loss function, or how the model knows how it's performing, is the MAE, for example, the error between the results and the actual values. So in this case, you finish, the performance of the model is really bad. But then you keep it because this is your baseline for comparison. Then you move to another machine learning algorithm that's more complicated. For example, you move to random forest, you move to XGBoost. The good thing is that these models work the same way in all kinds of data. And they are very limited number of models used now. So now most papers you will see that they go over 3 or 4 different algorithms, and it's the same algorithms every time. So this kind of becomes a habit. You start with a simple model, you go a bit more complicated, and then you go with the best performing machine learning algorithm that's usually apparent in your research papers. Let's say it's XGBoost. Once you get to this point, you would know this is the best result you can get from this data set, from this design of the problem. After this, you have 2 routes you can go to. It's either your variables are not enough. For example, if you're trying to predict rainfall, if you use only humidity, that's not enough variables. So in this case, you can either go back to the research and see do you have better variables or not, or you can try to go with the same data set, but go with a more complicated approach like deep learning. So in this case, you can take your data set and start with a CNN network and see if deep learning can capture these patterns better than machine learning or not. In this case, if even deep learning gives you bad results, that means that you didn't provide enough variables or enough data for the patterns to be recognized. So in this case, you either have to add more variables or you have to add more data. The data is not sufficient in this case. But don't be discouraged when you get low performance model. This is usually the standard first step. Usually if you have a model and it performs really well from the first time, most likely there's something wrong. Does that answer your question?
Yeah, thank you so much for the question. So, first, we have to do some train validation and
Yes.
test. After that, we have to do some bias correction, I think. So, yeah, thank you so much for the question.
Thank you. Thank you so much.
Is there any other
The tutorial?
tutorial? Okay, let's come to the tutorial to use artificial intelligence in marine fisheries.
So we have 2 main tutorials, one for machine learning and one for deep learning. I tried to make it as simple as possible. So one thing, don't be overwhelmed if you don't get all the concepts here. Usually for someone to get to the point of doing this tutorial, it takes a course. So usually people learn this over a few semesters, but it's good to know what kind of steps are there for a typical machine learning or deep learning algorithm. The media that I'm using is Jupyter Lab, and it's very convenient if you want to perform data science or AI using Python. This, as you can see, you can add text, you can add images, you can add code and see the output of your code all in one place. So the output, the notebooks that I put in the Google Drive is the notebooks for this tutorial. If you want to see them, you can sign up for Colab. So Google Colab is one of the softwares or solution where you can just upload this notebook and see the output. Even if you want to change some of the code, if you want to start experimenting, you can use it as well and have all of your data in the cloud. It's completely free, so you can use it even for training. Okay, so let's get started. For the machine learning tutorial, the example that we'll be going over is the fish habitat modeling or PFG style hotspot mapping. So similar to the map of the big eye tuna prediction that we saw earlier in our application, I would give an introduction on how to create this kind of maps from the training to the prediction. So what we'll go over on this data set, on this tutorial, is that we will use big eye tuna catch data set and environmental data to be able to build a simple workflow for machine learning. So let's explore how our data set looks like. So this is data set provided by the Indian Ocean Tuna Commission. It shows different catch records from the Indian Ocean, and these are the kind of variables it shows. It shows the date, the location, and also the effort or how much time did the fishermen spend on a certain location, how much fish they got, and how many time they spent on that location. And then I added the kind of the ocean parameters, so the temperature, the chlorophyll, the salinity. So in this case, so we want to predict the fish amount for the big eye tuna in the Indian Ocean. One of the steps that we can start with is checking relevant research. So in this case, I used the variables suggested in Professor Mukti's paper, the implementation to create the, it's called HSI, the Pelagic Hotspot Index. So one of Professor Mukti's papers suggested that one of the most relevant variables that affect the distribution of big eye tuna is the temperature on the surface, and then the temperature at 200 meters, the chlorophyll on the surface, the sea level anomaly, and then we have other parameters that might be relevant, which is the thermocline, which is the depth of the ocean where the temperature suddenly changes. And then we have IOD indexes for the previous month. So if we have any, the Indian dipole indexes for the previous 3 or 4 months, it would show us what kind of climate events are happening in the ocean at that time. So in this case, we started with the relevant research. So we want to predict big eye tuna in the Indian Ocean. We start with papers that suggest what are the parameters that affect this before we start with programming. The second part is that we make sure our target variable or what we want to predict is relevant. In this case, let's say we have 2 fishermen. Both of them got 100 kilos of tunas in 2 different locations. But one fisherman got this fish in 5 hours and another one got it in 1 hour. We can't assume these 2 locations have the same quality. Clearly, the fisherman that spent less time was performed better. So in this case, to make sure our variable is suitable, we will calculate the CPUE, which is the catch per unit of effort. So if we have number of hours or number of hooks for the fishermen, we can divide the catch data by that number to get the similar to the average of the catch. So in this case, we will be predicting the CPUE or the average of the catch, if that makes sense. So our steps or workflow is always the same. We examine our data set, we visualize it, and we understand our prediction goal. So once you do this, this is already 20% of the workload. And then after that, our data set, similar to how we said earlier, we split it into 3 parts: training, validation, and test. The training data set is important for the model to learn. This is like the examples that you go over when you study. The validation is important for the model to know how well it's learning. So similar to the exercises that you do while you're studying. And finally, the test data set is similar to when you go take an exam. This is how the model evaluates how was the overall experience or how was the overall learning process. After that, we can use this data set to train multiple models. So similar to how you said before, we start with a very simple model and evaluate the performance, and then we go to more complicated models. Finally, we compare their performance and we create our predictions. So in this,
Oke, jadi ini nanti dia menggunakan beberapa variabel dalam data perikanan tadi, kemudian dia membuat step model itu ya, step untuk mengenerate modelnya. Nanti kita lihat ini script nanti akan dipakai. Jadi coba kita lihat bagaimana machine learning dikembangkan dari dataset yang ada di website itu ya, IoTC itu data tuna ya, yang kita dapat free itu ya, bisa kita buat sendiri, kembangkan sendiri. Ini coba kita lihat stepnya, ini hanya mencontohkan saja bagaimana model artificial intelligence bisa dikembangkan. Okay, please continue.
So here we will be using Python, and in this case the tutorial is divided where each section has the implementation of what this section does before. So if you're not familiar with the syntax, that's completely fine. You can use ChatGPT, Gemini, and copy the code and ask it to explain each section. And then you can tailor these sections to your case. So if your data is different, if your variables are different, you can find out what area you can change for it to work with your case. Also, if you work with different programming languages, you can also use these tools to give it the code and ask it to change it to your language. So if you're using R, you can upload this code to ChatGPT or Gemini and ask it to give you the equivalent in R or the equivalent in MATLAB. So the first section in every case and for all languages is the import of the modules or the functions that we will be using. So in this case, we have modules related to the data, how we will be loading the data. We have modules related to plotting if we want to visualize. And then we have a module for machine learning and data pre-processing. In this case, we use a module called sklearn or scikit. So this is one of the main modules that are used for Python machine learning. So regardless of what your area is, what your problem is, you will be using these same modules and these same functionalities. So the more you use them, the more familiar you will be with them. So first step, we load our data set and we examine the columns or we examine the variables. Like we saw in our data set from the IOTC, we have the date of the record over the catch record, we have the coordinates, the longitude, the latitude, and we have both the effort of the fisherman and the catch amount. So in this case, we will be creating a new variable, which is the catch per unit of effort, and it divides the total catch over the effort to be able to get some sort of average of the catch in that location. So this is what we want to predict. This is what we want to learn, the CPUE. And then we have our variables that are relevant to this particular target. So similar to how the research suggests, that surface temperature, the temperature at 200 meters, the chlorophyll at the surface, and the sea level anomaly, as well as the thermocline and the IOD indexes. So now that we have decided our input, our output, we can start with checking if the data has any problems. So one of the main problems that we encounter in our data set is missing values. So we have to make sure that we don't have any missing values. And if we do, we remove the records that have these problems. So now we can examine in each of our columns which ones has missing values. As we can see here, none of them has any missing values, so none of them is null. The next step is we visualize these cache locations. So to make sure that this doesn't have any problems, we can visualize the cache location, at least to get an idea about the spatial distribution of our data and where it's extended. So this code block, we give it the name of the columns and the name of the columns that have the coordinates, which is lon and lat in this case, and it shows us the the distribution of the data set. So this is how the data set is expand in this case from the IOTC. So it expands over this part of the Indian Ocean, the western part. So now we know what area does our model covers. So for example, here we can see none of this data set is around the East Indian Ocean. So most likely later on, they won't generalize to this area well. So this will help us in figuring out our limitations of our model. Then we examine how this TPUE changes from one month to the next one. So here we can see, because the IOTC provides accumulated catch data, so the same location, they give monthly catch records. So we can see some of these data sets, they span across wide variables, wide values, and some of them, they have a much smaller range of data. Like for example, in June, we have a very tight range of our catch data, while some months like April or August, the data is spanned much more widely. So now we've loaded our data, we inspected it. Next, we define our modeling goal. So in this case, we want to predict the CPUE per effort. We want to know how much fish we can get in a certain location. Because we are trying to estimate a value, this is a regression problem. If we wanted to classify the area, is this good catch area or not, this becomes a classification problem. So based on whether it's classification or a regression, we define the loss function. So earlier we mentioned that the loss function is necessary for the model to evaluate how well it's learning. So in this case, because we are trying to predict an amount, the metrics that we can use is MAE or RMSE. So we can check the absolute error, or we can check the root of the mean square error to see how far or how close we are getting from the ground truth. We have also another indicator called R-square. This will show us how much of the variation is explained by the model. And the target in this case to get as big as possible. So if our R-square is close to 0, that's not ideal. The closer it is to 1, that means the model, the model explains well our data. If we have a very small R-square indicator, that means the model doesn't explain our data well. That's why we mentioned earlier that the accuracy is not always the only indicator how well our model is. We can have a model that's really well, has really high accuracy, but if the R-square is very small, that means this model doesn't explain the data and probably won't generalize well outside of this. So now we have decided how we can evaluate our data set. Now we can move on to choosing the columns that we will use for training. So now this is something very crucial, and it's excluding the columns that might cause a data leak. So a data leak is similar to you taking an exam and performing really well on the exam, but while cheating. So that means leaving variables that might cheat the code or cheat the model into getting the right value without actually learning. How is this? So now, for example, we want to predict the CPUE, which is the average of the catch over effort. If we leave in the X variables the catch amount, that will give the model a way to cheat. For example, the model would just look at how much catch was the total and would be able to tell most likely the CPUE because it's just simple division. So in this case, we have to remove all columns that would help leak some information about our variable. So in the earlier data sets, we would remove every other column. We would only leave two sets, the X and the Y. The Y in this case is our CPU-E, and the X is all the environmental variables that would help. So the temperature, the chlorophyll, the sea level anomalies, we would only leave these two sets of variables. The next part is the train validation test. So we loaded the data, we inspected it, we cleaned it, we decided our X and our Y. Now we split the data set to train, validation, and test. So this is the main step that would be in the training of all models, regardless of the problem. So the training data set is used to fit the model or train the model. The validation data set, it will show the model how well it's learning. So while it's learning, the model can adjust the approach based on the validation data set. And finally, the test data set is the data set that we will use for final evaluation. So if I tell you my model has 30% accuracy, that means the test data set had this accuracy. So now that we have split the data set, this is one of the models that are ready, the modules or the functions that split the data set. It's called train, test, split. So we only give it the data set and the percentage that we want for the split. So for example, in this case, we can choose that our training data set can has 50% of the data, and then the other 50%, we can split it into 40% test and 60% validation. You can choose any split or any percentages that you want to go with, but you should at least use half of the data set for training, and the other half is for validation and testing. So once you use this function to split the data set, then you can start with your actual training. So the first model, before we start with the training, we can have some helper functions that would help us evaluate while we're proceeding. So one is for evaluation is calculating the metrics. So earlier we said we would be using the mean square error and the mean absolute error for evaluation. So we have a function that would take the ground truth and the prediction and calculate this. And the second part is for the plotting. So plotting the relationship between the ground truth and the predicted. So the models that we will be choosing is, we'll start with a simple model, linear regression, let's say. So linear regression is good because it's interpretable. But because it's simple, usually it doesn't give very good results. So the steps are always the same. We load the model, we fit the training part, and then we predict the evaluation and the test. So here we loaded the model, and in this case it's linear regression. And then we give the model the training part, which we give it both the X and the Y. And finally we predict for the evaluation data set, so the validation and the test. So here, when we check the evaluation of the linear regression, in this case, we can see that these are the values it accomplished. So notice that in R square, in this case, the performance was 0.6 for the validation and 0.58 for the test data set. So this is not ideal, but it's not too small. So this is acceptable. It says that 60% of the data or the variance is explained by the model. So any change happens, 60% of this change can be well captured by the model. So usually in the evaluation, we check the metrics and we check the plot. So here, let's see the relationship between the observed catch amounts and the predicted catch amounts. So we can see in smaller value, the closer the points are to the diagonal, the better. So we can see that the smaller the values, the closer they are to the diagonal line. That means in this case, the predicted and the observed are equal. And this other part is the higher values. So we can see when we go higher, even if the observed variables change, the prediction doesn't change much. So this is the other 40% of the data that's not explained by the model. This same thing happens also in the test data set. So here we already finished the training for the linear regression. Then we move to a better model. So in this case, it's the random forest. So the random forest is a well-known model. It's a tree-based approach. And it's good because it can capture nonlinear relationships and also the interaction between the variables. It's more suitable for the complex environmental responses. So the same way, we load the model, we fit the training dataset for the training, and then we predict or evaluate the validation dataset and the test dataset. So when we check the metrics, in this case, we can see that the R square is much higher. So in this case, instead of 0.6, it was 0.65. So that means 56%, 65% of the data or the change in the data is explained by the model. As well as the error still stayed relatively low. So after we check the metrics, we can check the plot. So in this case, we can see that although for big variables, still there is no much correlation, but for the smaller variables, we can see that the circles are exactly on the diagonal line. That means that they're exactly equal. So that means the model for smaller values can get the exact prediction, and it would be equal to the ground truth. So this is in the validation dataset, but it also applies to the test dataset. So this model performs really well in the smaller range of the catch. In tree-based approaches, we can also check how important were the features. So after this model trained, it can tell us that what variables it used to get these results the most. So in this case, we can see that the temperature at 200 depth was the most relevant for evaluating, for predicting the fish. And then the locations, so where in the ocean the catch fall on, was the next important. And then the sea level anomalies. We can also see that the model didn't use the thermocline depth much. So knowing what depth the temperature change in wasn't very important. So after we evaluated this model, we can check another model. So the GAM, the generalized additive model, is useful when we expect the relationships between the ecological parameters would be smooth. And this was the model that was used by Professor Mukti in his publication to get the pelagic hotspots. So in this case, we also do the same thing. We load the model, the linear GAM. We give it how much variables we would be using. And then finally, we predict after we fit the training, we predict for the validation dataset and for the test dataset. So now we can see that the R square was a bit lower than the random forest. So in this case, the random forest performed better than the GAM, and the error was slightly higher as well. If we want to examine the relationship between the prediction and the ground truth, this is the plot. So if we remember earlier, the points were exactly on the diagonal line. Now they're kind of around it. So that means there is a relationship or correlation, but it's not exactly accurate. The same goes for the test dataset. So it's important to check the evaluation in both the validation and the test dataset, because the test dataset is the kind of data that the model never sees while training. So this is like the exam that you go take. You have no idea what kind of problems there would be. So this is the proper evaluation for the model, the test dataset. The GAM also can show you how the fish catch amount changes based on the separate parameters. So here we can see how it changes with the surface temperature, or how it changes with the temperature at depth 200. So we can see, for example, at temperature 200, the catch increases up to a certain point to 15 degrees. But after it increases, the catch reduces. So that means the most ideal temperature at 200 depth is around here, 15. The final model that we would be using is XGBoost. So XGBoost is one of the best tree-based approaches. They work really well on tabular data sets, and it's not as interpretable as the linear regression or the GAM, but it gives very good predictions. So the same way, we load the model, we fit the training data set, and we predict the evaluation data set. So here we also see the R square was very similar to the random forest and the GAM. And when we plot the data set, we can see that it's exactly aligned. So it exactly overlays the diagonal data set here. So that means it's more accurate. The same goes for the XGBoost. Finally, we compare all our models. So now after we cleaned the data set, we tried different models that were very dominant in our research papers. And we can order them by the error or the R-square. So we can see here the best performed model was the XGBoost based on these metrics. It was the one that had the least error. So when we are predicting, we usually go with the best performing model. So in this case, the XGBoost. So how can we use the predictions? So this also shows the relationship between the prediction and the actual amount. So this is how the values were different. So we can see that they are very similar up to maybe the 5th fracture. Now if we want to create the maps, we would know that the X variables that we used were the temperature, the chlorophyll, the sea level anomalies, and the thermocline. So let's use this on the same data set that we had for the test section or the test sub-data set. So the same way we can load the test part of our data sets. Oh, a second. So here we load them the same way, the subset of test subset. We load the environmental parameters, the temperature, the chlorophyll, and so on, and we give it to the model, and the model gives us these predictions. So when we compare this with the original data set for these points, we can see the areas that had the brightest colors. I don't know if they show, but these areas, they align with the original ground truth data. So this is the ground truth data. It reports the highest catch is around this area. So our predictions align with that. If we want to expand and create a bigger map, similar to the one that we show in OE view, we load this model on each pixel or each location. So in each location of this data set, we try to find the temperature at the surface, the temperature at 200, the sea level anomalies, the IOD indexes, and we take these as X variables and we give it to the model. The model gives us the CPU-E, and we put the CPU-E value in that area. So in this case, for simplification of the view, I rescaled the values between 0 and 1 to give us kind of an indicator of which areas has the highest catch. Then we would get this kind of maps. So in every case, the approach is the same. We clean the data, we split the data into training, test, and validation. We load the models, and then finally, after training, we do the prediction. Once we get a model we are satisfied with, for the same logic, we repeat the process by choosing the variables for the prediction. We give the input to the model, and the model gives us the output. The only difference is that during training, the model can see our predicted data, which is the CPU-E, but while for prediction or for forecast, the model usually doesn't know the CPU-E. So in this case, for example, we want to predict the big eye tuna for the following day or for the following week. In this case, we don't know the catch, so we can give the X variables to the model, and the output would be the estimated catch on that specific day. So this is it for the first tutorial. If there's any questions, we can take them or we can go for a break.
Ya, saya kira menarik ya. Jadi satu data set itu dia bisa bangkitkan menjadi peta prediksi dengan 4 model begitu ya. Jadi diseleksilah dari 4 model itu data set 1 ya. Itu diseleksi yang mana yang paling cocok. Nah, ini kan this is just use Python script.
Yes.
Ya.
Yes.
Jadi menggunakan satu script saja, Python saja yang dia pakai sudah bisa membangkitkan beberapa model alternatif begitu. Yang mana yang paling sesuai dengan data kita begitu. Kalau kita memprediksi itu tergantung dari jenis data kita. Nah, kalau data kita lebih cocok dengan model yang satu, yang model itu yang kita pakai begitu. Jadi tergantung distribusi data masing-masing individu begitu peneliti. Dan ini menariknya bisa dilihat dari berbagai macam pilihan itu, bahwa yang mana yang paling cocok dengan data kita itu yang akan kita pakai. Baik untuk penelitian dan publikasi juga nanti untuk adik-adik mahasiswa yang di pasca. Saya kira menarik untuk satu kali merunning saja sudah bisa melihat gambaran kira-kira hasilnya seperti apa yang bisa kita. Ada pertanyaan barangkali sebelum? Ya, silakan Tia.
Thank you so much for the tutorial. It's so very insightful for us. Can I ask why XGBoost is better than the other? Because I saw the value of the R square of random forest, it's higher than XGBoost. So why XGBoost is the better for the other? Thank you.
Thank you. So usually for evaluation, we can go with the R square, but in this case, you can see that most of the R square were around 0.6. So here, for example, the XGBoost was 0.638, and then maybe the random forest was 0.65. So the difference is very small. So it's not very relevant. So, but for example, if the XGBoost was 0.4, then in that case, that difference is big. We definitely go with the one with the higher R square. But if the R square are similar, then we decide to go with the error. We evaluate based on the error. So in this case, we have two kinds of error, the absolute error and the root of the squared error. So the XGBoost was the one that had the smallest RMSE in the test dataset and validation dataset. But even in this case, when the performance of the models are very close to each other, you will see that the results the prediction would be very similar. So even if you use another model like the random forest for the prediction, you will find that the results are very close, or at least the order of where the model tells you to go for fishing would be similar in both cases. So in this case, maybe it's better to evaluate based on your case. Like for example, in fishing evaluation, we know that some years are problematic. So if we have a climate event, for example, happening in one year, that's usually unusual because it's outside of the normal distribution of the ocean parameters. So in this case, we evaluate based on these unusual cases. So we can take both models and we create the maps for years where the climate was different. And we see which one performed better in our case. So there are multiple ways you can evaluate, but when the results are similar, that means most likely the models will perform kind of in a similar way.
Thank you so much.
Thank you.
This is also PhD candidate.
Oh, really? Oh.
Maran-san, this is PhD candidate in Kyoto University in informatic engineering.
Good luck on your thesis.
Okay, any another questions? Is it okay? No?
Yeah. So let's take a break. Let's take a break for prayer for 10 minutes. Is it better or should we continue?
Continue in deep learning.
Yeah. So the second part is for deep learning.
Oh, yeah. Kita mau istirahat dulu atau lanjut saja sedikit lagi? Okay, let's continue to.
Okay, so this is the first machine learning tutorial. As we could see that the data were in a table. So for every variable in every location, there was just one variable or one value. So in this case, these tabular data sets, the machine learning approach works better for them. But sometimes the data is more complicated for machine learning approaches to work. An example for this, when we are trying to predict fish, usually the temperature at the certain location is not enough. Usually we need to check all the surrounding locations. So not only the temperature in your specific location, but the surrounding area, because it will affect how the fish migrates or moves. So in this case, machine learning approaches is not enough because just one value for the variable is not enough. this is where deep learning is useful. So deep learning can be used to analyze any kind of complicated data. So how your phone works when it tries to recognize your face when you log in, this is a recognition model trained using deep learning. So any model that uses images, that uses voice, that uses satellite images, where the data is too complicated, a deep learning structure is used. So in this case, in this tutorial, we will go over loading satellite image dataset, and we explore them to understand them better, visualize them, and then when we proceed with the training, we do the same thing. We split the data into training, validation, and test, so the same logic. We decide what we want to predict, the same logic, and we decide on how the error would be like, or the loss function in this case. And finally, we evaluate the model. So the steps are the same regardless of your problem and regardless of your technology. So first, we import the modules that we will be using. So if you use Python, one really well-known library or module is called PyTorch. It has all the relevant functions that is needed for training a deep learning approach, deep learning structure. So in this case, we would be loading the module for data, NumPy, or for random selection. We would be loading modules for plotting, which is matplotlib. And our deep learning structure is PyTorch. So as you can see, all of the imports here had torch in them. And finally, for the splitting of the data set, we will load the scikit or sklearn from earlier. So first, let's load the data set. In the directory, in the QR code I shared earlier, inside it has a folder called tutorial2. Inside that folder, there is a folder called Eurosat. So this is our training data set that we will be using. So Eurosat is a satellite that uses images extracted from Sentinel-2. So all the images for regions from Sentinel-2 is loaded in Eurosat. And this data set has images that have the size 64 by 64. So the difference here is that instead of the input being one value, the input becomes an image or a small image. So this data set has different kind of images. We have images of forest areas, images of rivers, of highways, of agriculture land. So different images captured by the satellite. And in this data set, each folder has one category. So the structure of our folder would be something like this. We have a forest directory, river directory, residential areas, and so on. So this is the data set. So let's visualize. So this code block visualizes the data set. We give it the name of the folder, and then it loads samples from these different data sets. So here we can see the number of the images is 27,000. So this data set has around 27,000. And the classes or the labels of these classes, of these images, is 12. So we have forest, highways, industrial, pasture, so 12 classes or 12 labels. So before we look at the images, we want to know how the images are presented in computers. So what makes a data kind an image? So usually if we have one variable or one value, for example 7 or 10, in this case this is just one dimension and one value, right? Or in some languages they call them dimension 0, so just one value. An image usually is a representation in 2 or 3 dimensional format. So if the image is black and white, it's usually a matrix of 2 dimensions. So for example, this image that we see of the forest, this is a 3-dimensional image. Why? Because it has colors. So to represent any colored image, we need 3 channels. One channel would show us the values in the red channel, in the red tire, and the other one would show us in the green channel, and then the last one in the blue channel. So for example, if we see a pixel here that's white, that means it had the maximum value in the red, in the green, and in the blue. Similarly, if we see a pixel that's completely red, that means it had the maximum value in the red, but the minimum in the green and the blue, and so on. So this is how the images are represented. So we can see, for us, this looks like an image, but the computer sees it as a 3-dimensional matrix. So the first layer is the pixel values in red channel, and then the green channel and the blue channel. So how is that relevant? It's relevant because for us, recognition might be very simple because we already recognize what in the picture here. But for the model, it's a bit more complicated, or for the computer, because it has 3 dimensions. So this image becomes a 3-dimensional array. The first dimension is the number of the color channels. The second one is the height, and the third one is the width. So now let's look at the pictures in our data set. So this code block will go over the directory and shows random pictures from each class. So here, for example, we have the images from our crop in the first row. The second row has pictures from forests, so completely like green images. The third one, vegetation, so different kind of vegetation, but not forest. Then we have pictures of highways, industrial areas. So these are all the images that were captured by the satellite. In this case, they are given labels. So here in our dataset, we already know what each image, what the label is for that image. So from this image, we know that the purpose of this tutorial is classification. So we hope that by using these images and training it on the model would be able to recognize what kind of category the image belongs to in the future, even without knowing the ground truth. So now that we looked at our data set, we saw the different labels, we know that the input would be the pictures, the output would be the class or the label. One thing that the deep learning can be different in from machine learning, if you can remember earlier in the CPUE estimation, we already gave the variables for X. So we already knew what parameters affect the catch amount, whether it was the temperature, the chlorophyll, the sea level anomalies. For deep learning, sometimes we don't need to give any variables. So we can just say that these pictures, they have some patterns for each class, recognize them and let us know. So we can just give it the pictures that are organized, and the model would give us the predicted label without us sharing any insights. This is similar to knowing that, or saying that I know there is a pattern between the different pictures of the same class, but I don't know what. You find it out and let me know. So now we start with the splitting of our data set. So in this case, the data set was a bit too big. So instead of 27,000, I sampled only 6,000 for the training of the model. So now we have defined our data set, its images that are 3-dimensional because they are pictured, they are colored, sorry. And we defined our variable. So what we want to predict is the label of the image. So my goal is that I want to create a model. If I give it a picture, it will give me the label of the picture, of the class of the picture. So the first step is that similarly, I would split the data set to training, validation, and test. Regardless of the structure of the model, this is necessary for the model to be able to adjust the learning process. So in this case, we will use 70% of the data set for training, 15% for validation, and 15% for test. So this code block does exactly that. So it splits it first to the 70% of the training, and then the remaining, it splits them half for test and half for validation. After we created our subsets, now we define the structure of the deep learning model. So similar to how we said earlier, the deep learning structures are structures that replicate how our brain works. But this is kind of complicated to design or program. So the way that we approach it is that, let's say we have a picture of a dog. If we see this picture, it's very easy for us to recognize that, okay, this is a dog. But if we try to program this, we would take a lot of neurons which what we said earlier, a neuron is like a small structure that holds very small amounts of data. They communicate with each other to generate intelligence or generate recognition. So we structure them by the first layer, we put them, and we say, okay, the first layer of neurons, your job is to, let's say, read the pixels. So read the amount of the value of the pixels. The second layer, we can say that, okay, your job is to recognize the edges. So if I asked you, how do you know this is a picture of a dog? You might tell me that the color is of a dog. So the first layer recognizes the color. Someone else might tell me, I know because it has the outline of a dog. So the second layer identifies the edges. Someone else would tell me that the texture is of a dog. So the third layer would recognize this, and so on. Eventually, we would reach the conclusion that, okay, this is a picture of a dog. But the good thing is that in this case, I wouldn't tell these layers what to learn. I simply would put like a lot of layers of neurons and then leave the model to learn on its own. I wouldn't tell it what it should learn. So I would simply just give it pictures of dogs and the structure of the model and leave it to learn on its own. So this is a code block that has this full picture. It's just simplified here. So this whole code block creates a convolutional neural network. So the relevant parts here are these three functions. So the first function is called convolutional 2D. So the purpose of this function is to detect patterns. So simply, if we want more detection, we can increase the sizes of these convolutional networks or these convolutional layers. The second relevant layer is the ReLU function. So the ReLU function is similar to how, if I tell you, focus only on the important patterns. So highlight only the important clues and ignore everything else. And the third part is called max pooling. So for the max pooling, it's like I'm telling the model, don't ignore everything else in the data, only leave the strongest clues. And finally, we connect all of this to look at all the clues and decide together. So this is basically the simple explanation of the structure. So first I recognize the patterns, then I focus only on the important clues, and I ignore everything else. So this is only one structure of neural networks. As we mentioned earlier, we have multiple structures for how we can order our layers, how we can decide which ones communicate with which ones. And usually each of these networks have a name. We have ResNet, we have UNet. So we have multiple names of different structures that are usually known to work for specific cases. So now that we have defined the structure of the model, we can define the other functions that are needed. So before we mentioned for any learning process, a loss function is needed. So the loss function is the representation of how well the model is learning. So earlier it was the absolute error or the mean absolute error. For the classification problems, now in this case, this is a classification problem because we want to classify different areas. The loss function would be the cross entropy. The optimizer is how the model adjusts its learning process. So earlier we mentioned that we have training dataset, validation dataset, and test dataset. And the validation dataset is important because it teaches the model how to adjust its learning. So it adjusts its learning by this function, the optimizer. So I don't get involved at all. I just give the model the optimizer, and then I hope that it adjusts the learning process based on this optimizer. So these are the three things that are necessary for like a deep learning structure. First, we need the structure itself, in this case, the convolutional neural network. Then we need the loss function, which is how the model would be evaluating how well it's learning. And finally, we need the optimizer. So just a function that I would give the model to organize itself. So in this case, if the loss function becomes too big, the optimizer steps in and tells the model, okay, you are doing something wrong, go back. If the loss function is too small, the optimizer would tell the model, okay, you are going in the right direction, and adjust the weight of the parameters similarly. The good thing is that all of this happens inside a black box. I don't need to step in at all. So now we start with the training of the model. So the training of the model is different from the machine learning because it works by a repeated process. So we have something like loops, it's called epoch. So in every epoch, the model predicts some labels, or in this case, it just guesses them. So it guesses the labels, and then it calculates the error. And based on this, the optimizer changes the parameters' weights. So this is what happens in every loop. So every loop, the model guesses. If it guessed correctly, the weights are adjusted. If it guessed wrong, the weights are also adjusted. So this code block, these few lines, this is how the model learns. So as you can see, you didn't really step in, you didn't examine anything inside, you just basically told it to go for 5 loops. So usually in every loop, I monitor the loss. So to know if I'm going in the right direction or not, I print out my loss. So here we can see in the first epoch, the loss was 236, and then it became less, 185, and then it became 164. So what this tells us is that in every loop, the model is learning more and the error is becoming less. So usually this is the concept that we talked about earlier, the underfitting and the overfitting. If here the loss is always decreasing, that means the model is learning on the validation dataset or the training dataset. But then if we evaluate on a test dataset and the results are not as good, that means the model is overfitting. So it's basically memorizing the data more than learning from them. So here, just for an example, we went over only 6,000 of the data and only for 5 loops. Now we evaluate. So the test dataset will evaluate on the part of the data that the model has never seen before. So here, how do we evaluate? We have, we check for every image, how the model is going to classify it, and we check the correct classification. So here in this block, or in this code section, we will print out the image, we will print out the actual classification, and we will print out what the model predicted the class to be. So here, for example, this first picture, it's an actual forest, and the model correctly classified it as forest. The same one as for the lakes. But let's look at this picture. The ground truth of this picture was an industrial area, but the model classified it to be residential area. So we do this for all of our test dataset, and then we calculate the accuracy, how much of the data was correctly predicted. So in this case, our accuracy is 66%. So in this case, the accuracy is the correct predictions over the total amount of predictions. So here, this is 66%. So usually, the next step would be is if we're satisfied with this accuracy, that's fine. If not, we can increase the number of epochs. So here we can see in this loop that the error was still being reduced. So from 160, 140, 120. So if we add more loops, the loss is going to become smaller, or the error is going to become smaller, and the model would learn more. So in this case, we can increase the number of epochs. Instead of 5, we can make it 10 or 20 or sometimes even 100. When do we stop? We stop when the error starts increasing. So here now the error is still decreasing, but once the error starts increasing, that means that the model stopped learning and now it's just getting confused. So usually we have to stop in the right point before the error starts increasing, but not too much. So if we notice that the error is not changing much between loops, that means that the model learned everything it can learn at this point, and we shouldn't go farther because now it's just going to start memorizing stuff. So now with only 5 epochs, the resolution, the accuracy was higher than 66. So now the interpretation of this is that we use these images for classification of the scenery. Deep learning is important in these cases because not only we can classify the satellite images, but we can also detect different ocean parameters. So for example, in this case, if the images were parts of the ocean that has a chlorophyll, for example, in this case, we can learn different patterns from this. Or if we can have the relationship between areas that are covered in land versus different areas in the ocean, then we can also do this kind of prediction. So this this example only used the land cover images, but the same technique and the same logic we can apply it to satellite images using sea surface temperature or chlorophyll or fronts and so on. So just to give like a visual, just to give you like an idea visually how the CNNs work inside. So earlier we said that this satellite images is like 3-dimensional number array. So usually what the CNN does is that the first step, it like filters, scans the image. This step is similar to, let's say, when you put on sunglasses, it's like you see the scenery in a different color. So in that case, sometimes some details might become more apparent and some details might become difficult to see. So it's like the model puts on different glasses every time, and each time it manages to pick different details. So every time it looks at the scenery and sees something different, it's called a feature map. So with the collection of the feature maps, every time the CNN learns something new. So just to show you, for example, this image, the original image that we see, because we already have visual comprehension, we can see what areas are the houses, which one is the lake, but the computer doesn't see this. So what it does is that actually it puts on different glasses every time, and every time it puts a different color, it manages to see a different images. So this is how the different filters can be seen. So for example, the first time it puts on this filter, this becomes the scenery. So now, for example, we use 12 kernels, so in this case, the model would look at 12 different images. So we can see here differently that some pictures show texture better than others. Some pictures show the edge parts better than others. So using these different images for all of the data set, the model manages to pick up how to see textures, how to see edges, and how to recognize the image better. And how do these glasses look like, or the filters? This is how it looks like. So in this case, these are the filters that the model uses, and they are called kernels because they are so small in size. Usually it's just 9 pixels. So it's similar to the model putting on the first filter or the first glasses and then scanning all of the image, and then putting on the second glasses and scanning all of the image, and so on. So by putting on these different filters or kernels, the model manages to learn something new from each filter or from each glass, if you may. So in this case, our deep learning model managed to look at different images, split the data set, and learn the classification of the different images. In this case, we can see it's different from machine learning because the size of the input was different. Before, we used to look at 1 values, but now we look at 3-dimensional arrays. So do you have any questions in this part? There's only one small part left. So if you don't have any questions, we can move to that part.
Thank you for opportunity. I'm very interested your explain about the deep learning. So I want to ask about the data collection. I mean, if the powerful the use deep learning can transformation the image, right? Such as the NDVI, such as NDBI. So what is the challengings when we transformation the image to get it the powerful result based on based on the deep learning data. Thank
So
you.
what are the main transformations you're interested in?
Like transformation image, like NDVI to combine
Different layers.
to combine red, green, and
Yeah.
blue the cellular of the satellite.
Okay, so the same way here, when we put these different filters, we saw something else. So here, for example, we can see that some details are picked on by red kernels or red filters. Some details are seen better by blue, and so on. We can see that usually the color filters change the information that's portrayed to the image. So in the satellite image, we have something else. So now the colored pictures that we see have only 3 channels. So these 3 channels based on the color representation. Usually the satellite images that we have, they have a lot more channels. So not only the normal RGB, but sometimes they get the SAR layers, they have much more channels. So sometimes 13, sometimes 12. So each layer or each channel, it shows you the information separate differently. Why? Because in these cases, it's not only colors, but it's also the wavelength of the channel. So this is how like the satellite captures these images. It gives each layer or each channel has a different wavelength. So it captures the image or it captures the view, but with different wavelength. So usually that's why, for example, in the Sentinel, we know that some layers show us smoke better, for example, but some layers show us the vegetation better. Because why? Because the colors of the smoke or the wavelength usually is different from the wavelength that we see when we look at green trees, for example. So usually the kind of channels that you choose depends on what you want to detect. So let's say you want to detect water surfaces. In this case, you target the channels that give you the most information related to water. If you want to, let's say, use satellite images to detect fires, in this case, you would look at the channels that are closer to the red or can detect small smoke and fire better. So these different filters that you use, it's not just the transformation, but it's the selection of the data. So from the beginning, you don't look at the 13 channels, you take only just a sample of. But of course, how the satellite providers give you these images, it has some transformation. So this data is cleaned, and how the channels are separated, it already has enough transformations. But when you take the data, it's already been processed. You can have other transformations by yourself. For example, now in this case, if I say the color is not relevant, I want to change it to black and white. So in this case, I can define a function, black and white, that changes the 3 dimensions to only 2 dimensions. So I ignore the RGB channels and just take one intensity value. You can have also other transformation to change the range of the values. So now, for example, if the temperature is between 20 to 35, I can average it and just give it between 0 and 1. Any process that you do to the data set after you choose it, it's called the transformation. Does that answer your question? Okay, thank you.
Okay.
Yeah.
It's completely.
Yeah. Okay, so the last part is the use of the spatial data set. So the images that we saw right now, these are colored images. It just has the color of the scenery. There is no location. So maybe these kind of images are not very relevant to you because most of the images that you will be dealing with is spatial data. So data that has location, longitude and latitude. Sometimes it has time as well. So this data set that you deal with, how do we change it to images? Right now we saw that the deep learning structures, they take images. So how do we change these files to that format? So what are spatial data sets? Spatial data sets are any kind of data set that has location information embedded in it. So for example, one of the format that is known for in marine sciences is netcdf files or geotiff files. So in this case, let's load one of these files and see what is inside. So in this case, we would be loading a file called from the Mercator Copernicus for temperature. So what kind of variables are in this file? We have first the time channel, what day does this file covers. We have the different depth. So we have, for example, surface level, 10 meters, 20 meters. And then we have 2 dimensions for the location. So the latitude and the longitude. So in this case, we need at least the longitude and the latitude to be able to look at the map, right? So let's load these 2 dimensions, so only the longitude and the latitude, and display them by order. So when we take the longitude and the latitude for the temperature file and we plot them, this is the kind of image that we find. So in this case, the value at every point represents the temperature at that location. So here, for example, the very bright areas that are kind of yellow, they are around 32 degrees. And the very dark areas almost close to blue, this is 25-degree temperature. So this is how you load netcdf files and make them images. So before we had a file that had 5 dimensions or 4 dimensions. When we loaded it, it became a 2-dimensional image or 3-dimensional image. So in this case, we have only the longitude, the latitude, and the actual temperature. How can we use this in a deep learning model? This image is too big, it covers everywhere. So if you remember earlier the machine learning approach, in every location we had just one value for the temperature. So what we can say is that in this case, instead of looking at only one location, maybe let's look at all of the surrounding area. So for example, in this image, if I have a location, how can I find the temperature there? So this image has 36 latitude values and 600 longitude value. So different locations in the ocean. How can I find one location in this grid? Let's take a sample location at -6 latitude and 110 longitude. It's close to Jakarta. So how can we find the closest pixel or the closest location in the image? We can use this code block to find the difference in each from each location, and the smallest difference, usually that means this is the closest location. So if we mark this on the picture, this location close to the Jakarta would look like this. So this location exactly. Before, in the machine learning approaches, if I want to estimate the fish here, I would take the temperature and the chlorophyll and the SLA, all of these variables in this specific location. If I want to use this in deep learning, I would look at all of the surrounding area. So similar to how I would cut everywhere from the map and keep only the area surrounding my point. So if I want to crop it, I would take a small area, so let's say 16 by 16, and cut everywhere else and only enhance this area. So this becomes the input for this location. So why is this important, or why is this relevant? Because in machine learning approaches, we need only one value for the location. So if I want to estimate the fish amount, we would just take that exact location and the temperature there. But if we want to use a deep learning structure, we need more information. So instead of taking the temperature at only that location, we have to look at all of the surrounding area. So that's why we would extract or cut all the surrounding area around that location. So the input would look something like this. So after we cut this, we can go back and apply the same kind of training that we did here. So as you see here, these kind of images were used to train the model. So if we use our spatial data set and we cut them to only give us the locations around our position or our location, we can use these patches of images and give them to the model to estimate the same thing. The only difference is that here in our deep learning approach, we wanted to classify the area, but usually for our spatial data set, we might be interested in predicting an amount. how much fish is there, what is the predicted chlorophyll there. Let's group these areas based on ocean parameters. There are multiple scenarios where we can benefit from that prediction. So this covered how we can change spatial data into images and then use the images for deep learning. Do you have any question here?
Ya, ada pertanyaan? Ya, jadi sudah ditunjukkan ya, dicontohkan penggunaan artificial intelligence pada machine learning dan deep learning yang lebih data yang lebih kompleks begitu ya. Dan contohnya tadi sudah ditunjukkan juga. Ada pertanyaan sebelum kita masuk ke sesi terakhir barangkali, yaitu mungkin closing statement ya. Ya, silakan Pak.
Thank you very much.
Thank you.
Maybe my question for the early your presentation. Is it this application can be more useful? Is it this application more useful for directly to goes to the fisherman, or we have to analyze first and then giving to the fisherman? Because I'm spec for the fishing technology for operation, and then I'm worried if this application can be not interpreted good well goes to the fisherman. Thank you.
You mean the OE view application, right?
Yeah.
So in the OE view application, it can be used in both
Sorry.
ways.
For example, that you mentioned before that you can predict the tuna fishing ground.
Yes.
Is it can be separately by species or depend on our data collection?
So if usually most fishermen don't have enough data to conduct training. Of course, the best scenario is that if a fisherman has data and we can use it to predict give them their own model specific to their operation, that's the most ideal. But usually fishermen don't have enough data. They don't record this much data, or they don't want to share it. So in this case, they can directly just use the map. So, but in that case, the map is targeted towards one species, because for each species, how different ocean parameters affect the distribution is different. So in that case, let's say a fisherman is interested in the big eye tuna, they can directly use the big eye tuna prediction map. But of course, the results won't be as great as if they provide their own data set, because if they provide their own data set, it will cover their area of interest, it will cover their fishing habits, the time there where they operate. But it will still be good enough because the map is trained on catch data from these areas, also from the same fish species. So it will still be good enough. If they can provide more data, of course, the better, but usually they're reluctant to share. So in that case, they can just directly use the tuna prediction map available in the application.
Okay, thank you.
Thank you.
Okay, I think we'll come to the closing statement for us. I think we have now reached to the end of today's workshop session. And on the behalf of Faculty of Marine Science and Fisheries, Hasanuddin University, I would like to express our sincere appreciation to our speakers for their valuable presentation, and to all participants for your active participations and enthusiasm. Okay, maybe Bu Rahma, before we close this session entirely, we will hand over souvenirs to the speakers. It's just letters from Hasanuddin University.
Thank you so much. Oh, thank you so much.
Okay, we hope that this workshop serve as a platform for future collaborations and innovation and knowledge exchange among researchers, practitioners, and also students in marine and environmental sciences. Thank you very much for your participations, and have a wonderful day. And we look forward to seeing you in next sessions and of this workshop series in the near future. Thank you very much.
Thank you so much for your time. I know most of you are fasting, so I know it was a long time, so thank you so much. And please don't get overwhelmed by all of the information we share today. Usually people spend like years for studying this, but it's just good enough if you got just 1 or 2 pieces of information. And if any of you has any questions related to the session, or they want to use AI for their thesis or presentation, and they would like some help, this is my email, so feel free to send me. No question is small enough or silly enough.
Oke, thank you very much. Terima
you so
kasih
much.
Kepada semua partisipan yang sudah hadir ya. Kita akhiri dengan mengucapkan alhamdulillah. Selamat siang. Assalamualaikum warahmatullahi wabarakatuh.